Welcome back to week 8 of the problem solving session for the Introduction to Fluid Mechanics course, and today we will again continue our discussion on the Bernoulli's equation. So if you remember, in the last class we ended up with the derivation of the Bernoulli's equation, seeing that it's a special case of your Euler's equation for steady case and flow line and streamline with inviscid and constant density. We also saw that if we impose the condition that the flow is irrotational, then the constraint of the flow being on a streamline can be removed to apply Bernoulli's equation. So we will carry forward our discussion on Bernoulli's equation and see some practical scenarios or engineering applications or engineering devices where Bernoulli's equation are used. Okay, so just to reiterate again, I will briefly go through the topics and the examples taken by Prof. Chakraborty in the lectures, just for a proper revision, and then I will discuss some problems that are related to this week's discussion that will be very helpful for you in the exam as well as in your assignments. Okay, so that has been the agenda for all the discussion that we had in these sessions, but still, just to reiterate for any new viewers to this course. Okay, so I think with that we can start today's discussion. There are very few students, so I hope other students will also join, but meanwhile we can maybe just start our discussion and hope that others also join. Okay, so if you remember, in the last class we ended our discussion with the streamline Bernoulli's equation in a streamline coordinate system. So as I mentioned in the previous class, that we will take one example just to clarify our concept. So let us take one example. Okay, so we have been given a velocity field given by this equation, that is v is equal to ax square I cap minus 2axy j cap. Okay, our task is to find the radius of curvature for this particular velocity field. Like if this is a velocity field and you can associate a streamline to this velocity field, what would be the radius of curvature of that particular streamline? That's our question. Okay, so let us see how we can solve it. Moreover, just to reiterate, it has already been discussed in the class, but just for a proper revision, maybe I think we can discuss it again, and if there's any doubt, you can of course stop and ask me. Okay, so we need to see whether the flow is incompressible or not, just to see whether the Euler's equation can be applied, the incompressible from the Euler's equation can be applied. To see, we find dou u by dou x, that is 2ax, and dou u by dou y is equal to minus 2ax. So you sum it up, you find the divergence of the velocity field to be equal to 0, so the flow is incompressible. Okay, so now we know that the acceleration field, let us say A, can be represented as ax I cap plus ay j cap. This is a 2D field, so we have two acceleration components, and these are in the Cartesian coordinate system. Okay, so similarly we can transform our coordinates from Cartesian to a streamline coordinate system. Okay, so a more rigorous way or more robust way of doing this is to find a relation between the streamline coordinate system and the Cartesian coordinate system, but there is also another way that is being discussed in the class. So I think maybe you can take an exercise to find way to transform between coordinate systems. Maybe you can look into it in some standard textbooks. I don't think it will be asked in the exam, but just for your own knowledge sake, you can maybe look into some standard textbooks for your reference. But nevertheless, let us proceed further. So we will proceed further with the example that was taken by as was discussed by Prof. Chakraborty. So let us see what we can do. So we know that from the Euler's equation of motion along the normal direction to the streamline, this is the equation that we have in our hand. We have that dou p by dou n minus dou p by dou n is equal to minus rho g dou z by dou n is equal to rho an, where an is the acceleration along the normal direction, normal to the direction of streamline, which is basically the centripetal acceleration or centrifugal acceleration. Okay, the component will obviously be the same. The direction will be differ. The direction of the acceleration will differ. Okay, if you consider centripetal, it will be inside in the inward direction. It will be centrifugal. It will be in the outward direction. Okay, so the main thing to note is that the if we know the normal acceleration component from this, we can find an is equal to minus v square by r, and since we know the velocity components, we can easily find the magnitude of velocity, which is v, and from that, if we know an, we can easily find r. Okay, so that's our task in hand. We have to find the radius of curvature of this particular streamline. So let us see whether we can find the acceleration components. So how to do that? First of all, we know that no matter what the coordinate system, the acceleration, the total acceleration has to remain the same. Okay, so this should be equal to same as the original acceleration vector. Okay, so let us find, since we have the velocity components along in the Cartesian coordinates, let us find the respective acceleration components in the Cartesian coordinate system. Okay, so we'll have ax is equal to u, since it is steady, so the time derivative part is removed, so we'll have ax is equal to u dou u by dou x plus v dou u by dou y. Just carry forward the calculation, just substitute the value of u and v here. You will find ax to be equal to 2a square x cube. Okay, similarly you can find ay as u dou v by dou x plus v dou v by dou y. Then substitute the value of u and v in this equation, so you will get ay as 2a square x square y. Okay, so you got the respective acceleration components. So the thing is, since I told you the acceleration remains the same, so to say, if you need to find the normal acceleration component, say an, you can simply multiply a with the unit vector in normal direction to get the component of acceleration in normal direction. Okay, so that's what we can do. But the thing is, to do that, you need to find the unit vector in normal direction. Okay, so right now we do not have any way how we can do that. But since we know that our velocity v is always directed along s, that is, velocity is directed along the direction of streamline, so we'll have this normal direction along the streamline direction is epsilon s cap to be equal to velocity divided by its magnitude. Okay, so this will give you the normal vector along the direction of the streamline. Okay, so you have es. Okay, but you actually need epsilon n cap. Okay, so to do that, what you can do is you can do a very clever trick that was given by Prof. Chakraborty. You can take a cross product of your k vector, k cap, that is your unit vector along the z direction, with your unit vector along the streamline direction. So if you do a cross product between the k cap and epsilon s cap, you will get epsilon n cap. Why? Because even if you're in the streamline coordinates, your z component from the Cartesian coordinate system remains normal to your streamline coordinates. Okay, that's why using that clever trick, you can find a cross product between k and epsilon s will give you epsilon n cap. So now once you get epsilon n cap, you can easily find an, because you know that a dot epsilon n cap will give you acceleration along the normal direction. Okay, so just give me 1 second. Just look into the formulas. I will be back in one minute. Okay, just look in the formula. I'm sorry for the delay. Let us proceed further. Yeah. So as I was mentioning, okay, let me just repeat. Since we know that the unit vector along the z direction in the Cartesian coordinates will still remain normal to your streamline coordinate systems. So using that, you can find your unit vector along the normal direction to the streamline. And once you have that, you can easily find your component of acceleration along normal direction by doing a dot product between the total acceleration and your normal and your unit vector along normal direction. Okay, so from that you can find an, and once you get an, you can easily find r, because you already know v square would be square root of u square plus v square. U square and v square you already know, so from that you can easily find the value of r using this relation. Okay, so this was one example. Let us see. Let us take another example. Okay, so you have a bent pipe. Okay, and width of your pipe or duct, in this case actually it should be duct, is b. That is, the width of the duct is b along the width of, along depth of this paper, so it is b. And the respective velocity components are given by v theta is equal to c by r and vr is equal to 0. So it is a 2D velocity field. You have the the axial velocity component and the radial velocity component. So radial velocity component is 0, so it has only one velocity component. This is only the radial direction. So you need to find the pressure difference between points 1 and 2, P1 and P2, and you need to find the mass flow rate. Okay, so it is given, then you need to find the mass flow rate, and given the flow is steady and inviscid. Okay, you need to find these two things. Okay, so the key to this problem, or key to discuss this problem, is to understand the effect of the curvature of streamlines. So if you remember from our previous discussion, that for the equations of or Euler's equation motion along the streamline coordinates, we saw that because of the curvature of streamlines, there can be a pressure difference. Okay, along with the hydrostatic pressure difference because of the depth, because of this curvature of streamline, there can also be pressure difference. Okay, but if the curvature of streamline is infinite, basically if the streamlines are parallel to each other and are straight and parallel to each other, in that case, let me go back. Yeah, in that case, dou p by dou n will be equal to 0. Basically, if r tends to infinity, this will be equal to 0. So dou p by dou n equals 0. So there will be no pressure gradient because along the streamlines, because of the anything other than your, there will be no pressure difference if the body force is not considered. Okay, so just keep that in mind, because we will be using this concept again later in today's discussion, like how the absence of curvature in the streamline can help us to approximate pressure difference between 2 points, given that the body force or the effect of body force onto the pressure gradient can be neglected. Okay, so please keep this point in mind. Maybe we will recapitulate it or come back to it in the later part of this discussion. Okay, so we need to find P2 minus P1, okay, from this diagram. So the pressure distribution along the direction of normal to the streamline can be found out using this equation. Consider that the body force is 0, so the body force term is disregarded. So now we have to find the velocity, that is v. Okay, the v squared, it is basically the square root of the squares of the velocity components. So in this case, v theta square and vr square. Since vr square is equal to 0, there is a radial component of velocity is equal to 0. So we will have v to be equal to v theta. Okay, I think it's quite well understood now. So we will have dou p by dou r, and yes, and direction normal to the streamline in this particular configuration will basically be the radial direction. Okay, so that's why we can take eta is equal to r. Okay, so dou p by dou r would be equal to rho v theta square by r. Okay, again, just to reiterate, I think it would be a good practice for all of you to look into coordinate transformations. I think it's a far-fetched topic for now as a basic fluid mechanics course, and personally me also, I find it a bit difficult to understand how to do this coordinate transformation. Like if just randomly it is given, it's very difficult for me to also find the coordinate transformation. I basically need a relation between the two coordinate systems, then only I can do the coordinate transformation. Say for example, your from cylindrical to, from Cartesian to cylindrical coordinate system, the relation would be, say, if you want to go from, let's just give you an example. If you want to go from Cartesian to cylindrical coordinate system r theta, then the relation is r would be square root of x square and y square, x square plus y square, and your theta would be tan inverse of y by x. So this is the basic relation of coordinate transformation between the two coordinates. Now you have to accordingly change your governing equations depending on these coordinates. Okay, for me now, since I know a little bit of calculus, I can easily do the coordinate transformation, and there are again some standard laws or standard equations that have been already derived to do the coordinate transformation from one to from one differential for a, sorry, to do a coordinate transformation for a differential equation. There are some standard equations already given, so we can use that. But to understand it, I think for better understanding, I think you can just look into some examples where they do the coordinate transformation. Okay, so that will give you a better idea. Even if you don't know it or learn it properly, at least you have an idea like where the coordinate transformation has been done. Okay, so in this case, your eta is basically equal to r. That's the coordinate transformation. Okay, and since we're only dealing with the coordinate the transformation along the radial direction, or the normal direction to the streamlines, this transformation is enough for now. Okay, that's why I'm saying it's a simplified course, basic course, so I don't think you would really need it, but just for your own understanding or own interest, you can look into it once. Okay, so let us proceed. So now we have dou p by dou r is equal to rho v theta squared by r. Now v theta is c by r. If you remember, let us go back. V theta is c by r and v r is equal to 0. So v theta is c by r. Okay, just substitute the value of v theta in this equation. So you will get dou p by dou r is equal to rho c square by r cube. Okay. To find the pressure difference, you just need to integrate this equation now. Very simple. So you will have p2 minus p1 to be equal to c square rho integrated from r1 to r2, integration of r2 minus 3 dr r1 to r2. Okay, so just carry forward this integration. I have shown you the steps as well here. So once you do that, you will get p2 minus p1 to be rho c square by 2 times r2 square minus r1 square divided by r1 square r2 square. Okay, so you get this relation for your pressure difference in terms of your given parameters in the question. Okay, so that's your final answer. But, and of course, if you want to find the mass flow rate, again it will just be rho v theta b dr, because see, your v theta is the only velocity component in this case, and the area of the duct would be simply be b times the distance r1 and r2. But since the velocity is varying in this region, you cannot just simply multiply it, or you cannot just simply get like multiply the area with the constant velocity. So velocity is varying in the axial direction, so you need to take the elemental area. Okay, so if you carry forward this integration, you will get m dot, or the mass flow rate, to be rho bc times natural log of r2 by r1. Okay, so this is your mass flow rate. But the interesting thing that I wanted to point out was the next case. Okay, so let me ask you to do an exercise, like just look into this velocity field. Okay, so there are many things that you can interpret. First is since the governing equation of motion is in the Euler's equation of motion, you inherently consider the flow to be inviscid, plus this is for the incompressible flow, so your density is also considered to be constant. Okay, considering that rho equal to constant you have considered as an incompressible scenario, then the two conditions are satisfied. That is, flow is steady. In fact, three conditions: the flow is inviscid, and the flow is incompressible, density is constant. Okay, so three conditions are now satisfied. The fourth condition was that if the flow is along a streamline, now we can apply our Bernoulli's equation as well. Okay, so the thing was that point 1 and point 2 has to be along the same streamline for us to apply Bernoulli's equation to find the pressure difference between the points 1 and 2. Okay, that's the thing. Can you give me just 1 minute? I will just come back. Okay, just give me 1 minute. Okay. sorry for the delay. Okay. So as I was saying, if point 1 and point 2 were on the same streamline, then you could have easily applied Bernoulli's equation to find the pressure difference between the points 1 and 2. Okay. No need to discuss the Euler's equation of motion. So, but you can now also remember, if the flow is irrotational, then you can apply Bernoulli's equation at any 2 points in the flow field. And given the diagram, it seems like 1 and 2 are not on the same streamline. Okay, it inherently seems like the points 1 and 2 are not on the same streamline. So let us see whether, or rather, I will ask you to do the calculation to see whether the velocity field given by these equations turn out to be irrotational or not. Okay, it is irrotational. Okay, I know it, but because this is an equation, basically an equation of free vortex. Okay, again a higher terminology. I don't think I should be using right now, but you will know you can easily say that this is a irrotational flow. And also you can do it, just carry forward the del cross V, just find del cross V. Again, just remember you have to do it for a cylindrical coordinate system, then you need to find the respective operators for the nebula operator. Okay, respective equations for the nebula operator. Once you do it, you will eventually see that this flow is irrotational. Okay, so since now all the 4 conditions are satisfied, the flow is steady, inviscid, density is constant and irrotational, then you can just easily apply Bernoulli's equation. Correct? No harm in doing that. Considering that your duct is being placed like this, where point 1 and point 2 are on the same level, or same horizontal level, or same height, then Z1 is equal to Z2, so it can be easily cancelled out from both the sides. So we will have P1 by rho plus V1 square by 2 is equal to P2 by rho plus V2 square by 2. So P2 minus P1 will simply be rho V1 square minus V2 square by 2. And we know that since the radial velocity component is 0, only the axial velocity component exists. So V1 will be equal to V theta 1, V2 will be equal to V theta 2. Just substitute it. What you will get is then P2 minus P1 would be equal to rho C square by 2 R2 square minus R1 square divided by R1 square and R1 square times R2 square. Now if you see, these two terms are exactly the same. Okay, so we found out this without having any idea that whether we could apply Bernoulli's equation or not. Okay, and there's no harm in doing that. You started with the right fundamental principles. You know that your Euler's equation of motion governs this kind of flows. If the flow is inviscid and steady, you know the governing equation for that particular kind of flow. But you saw that there is some inherent difficulties, like if the geometry was a bit different, then again you do not know then you have to find the proper coordinate transformation to solve this equation. Okay, that's what I wanted to imply. But now, by understanding that these 4 conditions are inherently satisfied in this equation, you do not need to even look into any kind of specific equation of motion, be it Navier-Stokes or Euler. Okay, if these 2 equation of motion, if these 4 conditions are satisfied, then you can easily apply Bernoulli's equation between any 2 points and then find the pressure difference. Okay, so this I personally felt that was a very profound or important result. Okay, so I think I will stop here for 2 minutes, just for a bit of recapitulation and discussion. So if there's any doubt, you may ask. I'll wait for say 2 minutes, and then we'll have a resume of discussion with some more examples. Okay. Okay. So I feel there is no doubt then. So let us proceed further. Okay. So I think again we will discuss a similar we'll discuss a similar topic that was discussed in the previous class. The problem regarding the emptying time required for emptying of a tank. Okay, emptying a tank. So we already discussed a similar thing. So I think I can just quickly go through it because we already discussed this in the previous class as an example, which is basically the application of the unsteady form of Bernoulli's equation. Okay, so I think we can quickly go through it rather than what to say, dwelling upon it for a longer time. Okay, so this is the case in hand. You need to find the time to empty the tank, given that you have a opening of this form, like the first opening or the normal opening of the tank, and you say you have a small orifice at the bottom of the tank through which you are emptying the tank. Okay, your task is to find the time required to empty the tank. Okay, and the orifice may be placed here and here, anywhere at the point, and given the proper approximation, you can the similar laws can be applied. Okay, we will see how. So the Bernoulli equation in this case would be the unsteady Bernoulli equation because the four assumptions are satisfied, that the flow is inviscid and density is constant. The flow is not inherently steady in the case that for which you have to apply the unsteady form of Bernoulli's equation. Okay, so let us see. So this is the equation in hand. P1 by rho. I hope the diagram is clear. It's already discussed previously, but I think don't want to repeat each and every concept again and again. So maybe you can look into it. Okay. So again, there was some discussion on Torricelli's law. So I think I won't repeat it. Okay. That from Torricelli's law, the exit velocity during the emptying of a tank can be approximately found out to be square root of 2gh. Okay, so there is a detailed discussion on it. So maybe you can refer to a textbook by Prof. Chakraborty, that is the Introduction to Fluid Mechanics and Fluid Machines. You can kindly go through it once and find how this has been obtained. Okay, you will see that we can get the similar conclusion here as well, but we will not inherently apply it right now. Okay, so let us proceed. Okay, so for constant density flows, we know that the continuity equation reduces to A1 V1 is equal to A2 V2. Okay, and since the flow is inviscid, the velocity profiles at point 1 and point 2 can be taken as constant. No need to worry about the velocity profile. Okay, or integrating it around a particular area. If you see the flow is inviscid, you can easily consider the flow to be of constant velocity profile. Okay. Then V1 and V2 can just okay, that's what I will discuss. So from that you can find the velocity relations between point 1 and point 2, that say A1 is equal to A1, V1 is equal to V2, then V1 square D1 square is equal to V2 square D2 square. Okay, given that the area of the orifice as well as the opening of the tank can be approximated as circles. Okay, then we have V2 is equal to V1 times D1 square by D2 square. Okay, let me just go back to the diagram. Let us say the diameter of the opening of the tank is, say, capital D, and say the opening through which the tank is being emptied has a diameter of small d. Okay, in that case your velocity at the exit V2 would be V1 capital D square by small d square. Okay, and V1 can be approximated as, not approximated, can be taken as minus dh by dt. This is basically the rate of change of the height of the fluid inside the tank. Okay, so now comes the approximating term, that is how to approximate this term. Okay, so So we thoroughly discussed in the previous lecture or the previous problem solving session that this term is basically integrated along a streamline. Okay, this integration is along a streamline of length of length say s integrated with of over elemented area ds. Okay, so basically you know that the variation is considered along a streamline. Okay, but now the thing is, if you go back to the diagram, let us go back to the diagram. Say even if the opening is here, then we can easily consider a streamline to be of this form, like say from point 1 to point 1 to point 2, the streamline can be say of this shape or this shape or this shape. Okay, or even if say the opening was somewhere here, then also the streamline can be approximated as something like this. Okay, so what you can observe in all these cases is that the streamline more or less remains straight throughout the depth of the tank and only changes or only curves around the exit. Okay, and if the flow is in viscid, this change is again more abrupt towards the curvature, like it will be more abrupt towards the edges. Okay, so it will be more or less uniform and then suddenly change to exit through this orifice. Okay, or this hole. Okay, so with that approximation, and since the velocity then remains uniform along the streamline, then we can easily take this velocity derivative out of the integration and assume it to be a constant. Okay, so this is the approximation that we have to consider to simplify this term. Okay, so I can like this is what has been discussed in the class, and of course has been mentioned in the textbooks as well, so you can refer to it to make the proper clarification. Okay, so for your own understanding, I can suggest that you might look into different textbooks and their respective interpretations of how to simplify this unsteady term of the Bernoulli equation. But from the perspective of this course, and I think it's a very good approximation, you can simplify this term using this analogy or using this understanding. Okay, so now we have simplified this term. So now let us just substitute all these terms back to our original equation. Okay, so we have from the Bernoulli equation, unsteady form of Bernoulli equation, we will have v2 square minus v1 square by 2 plus g z2 minus z1 is equal to minus dv1 dt times h. Okay, and we know that z2 minus z1 will be equal to minus h. Let us consider these two terms to be say a and b. So what happens is that usually for if the say the tank is very very large and the opening through which the tank has been emptied is very very small, in those cases this term, that is b, the ratio of term b to term a, or the ratio of the magnitudes of term b and term a turns out to be very very small. Basically the magnitude of term b turns out to be very very small than term a. Then as a simplified case, as a very simplified case, you can consider this term to be negligible. Okay, as a first approximation. And if you do that, if you consider this term, magnitude of this term to be much lesser than the potential energy term, then you will have v2 square minus v1 square is equal to divided by 2 is equal to gh. Okay, and we know that from the continuity equation, v2 can be approximated as v1 times d capital D square by small d square. Then just substitute this value here, you will get v1 square is equal to d square capital D square by small d square minus 1 by 2 is equal to gh. Okay, or if you simplify it, if you just take these terms, all these terms in the right hand side, you will get v1 as c times root 2 gh, where c is this term. Okay, now we know that v1 is equal to minus dh by dt. Okay, this is something that we considered, we found out in the very beginning of the problem. Then to find the time, we just need to reorient this equation in a way. Just take this dt term in the right hand side and take this whole term in the left hand side. Given that c and root 2g are constants, you can just easily integrate both of these sides. Say integrate time from say ti to tf, and say integrate the height from hi to hf. Okay, just the variation. Okay, say if after the emptying of the tank, or not say emptying, I will say after certain instant of time, say after say TF, the height of the tank, height of the water in the tank has reached a value of HF. Okay, in that case you can have TF minus TIS minus of 1 by C times root 2G uh, integration of H half from HI to HF. Okay, just if you do it, you will get that this is the final form of your equation. Okay, the time required, and just like if say HF is equal to 0, like if the tank has been emptied, then take you can take Ti equal to 0 and HF equal to 0, then you will get the final form of your equation, the final time or time required to empty the tank. Okay, so I think I might have rushed here and there while discussing this example, so you might if you are in doubt, you can just ask me. Okay, I'll wait for a few minutes, then I'll proceed further, then we'll discuss the some applications of the Bernoulli's equation, the without tube venturi meter, and then we'll discuss some problems. Okay. Maybe I will just write it for your reference. Maybe something like, if you take initial time, say Ti equal to 0, then for an empty tank, HF would be equal to 0, right? So we will have T required, maybe something like this, would be equal to minus minus, we can cancel out, so 1 by C root 2 G times root HI. Okay, so this will be your final answer, or maybe 1 by C root 2H 2HI by G. Okay, something like this. Okay. So I will wait for 2 minutes here, just for me to also give rest to my throat for a while, and then we will resume our discussion. Okay, so I think we will take 3 examples or 3 scenarios in engineering application of your Bernoulli's equation. That is siphon, pitot tube, and venturi meter. Okay, and I will expect that you still remember the principle of manometry, so that will come handy. So I'll wait for 2 minutes, just for maybe you can just look back to your notes and see the principle of manometry, how the manometer, the pressure difference is measured using manometers. Maybe you can look into it, and then we will resume our discussion on application of Bernoulli's equation in engineering devices. Okay, we will discuss 3 examples. There are many examples if required, but for this particular session we will only discuss 3 examples, and I think that will be sufficient for you to be able to answer questions related to it in today's assignment. Okay. Just give me 2 minutes. You can meanwhile just revisit your notes on manometers. us continue our discussion. So, one of the examples that were discussed by Professor Chakraborty in the class for the application of Bernoulli's equation was the siphon. Okay, so siphon is basically used. It usually, like if I remember, is usually used for emptying tank using the concept of suction pressure. Okay, for example, you will see that. For example, if you want to extract, like for example, if your vehicle has the fuel tank of your vehicle has been emptied, okay, like the fuel like your fuel tank has become empty and you urgently need fuel and there is no say petrol pump nearby, then what people usually do is, like for example, if there's some other passengers nearby who are like traveling by a car or a motorcycle or any vehicle that has some amount of additional fuel left in their tank, so what they will do is basically they will insert a pipe in the fuel tank and create a suction pressure through the other end of the pipe. Okay, like for example, in this figure itself you can see that what they will do, they will say insert one of the ends of the pipe in the fuel tank, and in this exit they will create a suction pressure by, for example, by sucking in the fuel for a while, and then they will, once they create a suction pressure, the fuel will start to come out of the pipe's opening. Okay, and it's important to know that you have to keep the opening of this other end of the pipe lower than the level of fluid inside the tank. Okay, so once you have the suction pressure, this suction pressure will pull the fuel out of the tank and can be filled in a container, and that can be again used to fill the fuel tank of your vehicle, so that you can reach the nearby petrol pump and refill your tank. Okay, so this is one of the very day-to-day life application of siphoning, and of course for any researchers who are reviewing this session, of course there are n number of research where siphoning can be applied and understood in a much better way. Unfortunately, I am not working on siphoning right now, so I only have the very, very common example that I personally saw in my day-to-day life. So yeah, for the other viewers, I'm really sorry for being so limited to this example, but this is only example that I know right now. But again, there can be a number of applications for siphoning. Okay, but the principle still remains the same. To understand in a better way, let us again just apply. Let us just apply Bernoulli's equation in this scenario. Okay, so our 2 points to consider in this would be the free surface. The first point would be at the free surface of the tank, and the second point would be at the highest point of this pipe. Okay, like this point is at the highest point up to which the pipe has been lifted. So this let this be point 2. Okay, so it is important that the suction pressure is enough for the fuel to reach up to this point. Then only the fuel can be thoroughly being pulled out from the tank. Okay, otherwise if it's very, very high, then again it's very difficult to create the suction because the frictional losses will come into picture. But let us see, we are not considering that, but let us see what happens. So applying Bernoulli's equation between these 2 points, so we'll see that at point 1 pressure, if you just consider the gauge pressure, then at point 1 pressure is the atmospheric pressure, so we can just take it as atmospheric pressure, and the level of the velocity at which the fuel is emptied is again considered to be much lesser than the velocity of fluid exiting through the pipe exit. That's why V1 can be approximately taken as equal to 0. Then we have GZ1 is equal to P2 by rho. P2 we don't know right now, but we know it's the gauge pressure, plus V2 square by 2 plus GZ2. Now considering that the width of the pipe remains consistent, then velocity at point 2 would be same as velocity at point 1 because of the continuity equation, because area A1 is equal to A2, then V1 would be essentially equal to V2. Okay. So, and again using Torricelli's law, again is something that you can look into. We can approximate the exit velocity to be equal to root 2 gh. Okay, it's just a vague approximation, but let us consider that. Okay, then we have, yeah, from this we can take all the terms in the say left hand side. So we'll have P2 by rho to be equal to minus gh minus V exit square by 2. Okay, so now we can see that P2 turns out to be, since all these terms are positive, okay, H is positive. Okay, so you will see that this pressure, oh, H is not positive actually, so let us discuss it. So you will have minus Z minus G, yeah, it is positive, right? Z2 minus Z1, right, it is positive. Okay, so all the terms are positive, then we have P2 to be a negative term. Okay, P2 would be negative, but here P2 being negative does not mean that it is negative pressure, but it essentially means that it is a suction pressure, because it is lesser than the atmospheric pressure. That's why its pressure, the net value is negative, the gauge pressure is negative, means that it's a suction effect. So pressure here will tend to pull the fluid out of the tank. Okay, that's why the pressure value is negative here, creating a suction effect. Okay, but again now you can see that where the problem can arise in reality. So you will see that usually siphoning won't work always. Okay, there has to be a very ideal scenario that for siphoning to work, and after some time again the fuel stops coming out. Okay, that's also the scenario. Again you will see that primarily occurs because we are not considering the viscous effects at all, on the frictional effects in the pipe. Along with the viscosity of the fluid, the pipe surface also has some level of friction. So if that's the case, then again those two effects will tend to slow down the motion of the fuel inside or fluid inside this pipe. So that will essentially reduce the velocity and basically then stop the fuel or fluid to come out of the pipe. Okay, that will basically oppose the suction effect. Okay, then again there is one more concept that if suction pressure, your P2 turns out to be lesser than the vapor pressure of this particular fuel, of this particular fluid, then it can cause cavitation. But again, it's something just conceptual, one-liner understanding. If P2 is lesser than the vapor pressure of the particular fluid for the given pressure, given conditions, then it may cause cavitation. Okay, but it's just a one-liner topic of discussion for now. Again, if required for thorough discussion, maybe you can put that in the discussion forum, but I don't think it might be asked as a extended question in the exams, but can be remembered as a one-liner conceptual statement. Okay, so with that, let us now proceed to the second device, that is pitot tube. Okay, there is again a special device known as pitot static tube. Again, maybe something which I can leave as an exercise for you. So maybe you may want to look into pitot static tube as well. Okay, so all these devices actually, at least the pitot tube and your venturimeter, if like the participants for today's class are engineering undergraduates, especially if from mechanical engineering, these devices are your bread and butter in your fluid mechanics laboratory. Okay, so you will deal with all of them, and I am sure that it is a mandatory experiment in your fluid mechanics course. So I don't know whether any one of you have done it or not, but I think you will eventually do it. So if you have done it, then I think it's a good revision for you. And if you have not done it, now you will know what you have to deal with. Okay, so maybe it will help you out in your experiments as well, but let us try to see it. Okay, and that's why I was saying that in that fluid mechanics lab, pitot static tube also turns out to be a very, very fundamental device for experimental topic. Maybe you can look into it as an exercise, and if there is any doubt, maybe you can ask in the next class. Okay, so let us proceed. Okay. So what happens is that we know about piezometers. Okay, I won't repeat what piezometer is or what manometer is. We already discussed it in the first few lectures itself. I guess by lecture 2 or 3 we discussed it about the pitot static tube and about piezometers and manometers. That's why I asked you to revise your concepts of manometry. Okay, so I won't discuss it. The interesting thing is pitot static tube, which is a device of this form. Okay, as shown here, which is an L-shaped tube with a very small opening at its inlet. Okay, so this is the tube's inlet. So it has a very, very small opening. So what happens is that whenever the fluid, whenever it is inserted in a channel or in a pipe, and the fluid strikes this location here, what happens is that the velocity of the fluid, I'm really sorry for the pronunciation, the velocity of the fluid at that location, at the point at which it strikes this small opening, becomes essentially 0. Okay, so that's the most fundamental working principle or the fundamental concept behind the working of the pitot tube. Okay, so at this point, at point 3, at the opening of the static tube, the velocity of the fluid becomes 0. Okay, so we will use this very concept to understand the working or to understand the working of this pitot tube or the use of this pitot tube. So pitot tube is essentially used to measure the velocity of the flow inside a duct or a pipe, or even in an aircraft. Like they sometimes use pitot tube to measure the velocity of the flight, okay, of the airplane. So basically it measures the velocity of the fluid. Okay, so just to reiterate, remember, the purpose of using pitot tube is to measure the flow velocity. Okay, so in exams they might ask, what's the use of pitot tube? To measure velocity, to measure pressure, to measure temperature, to measure flow rate. Of course they won't ask temperature, but they might ask flow rate, they might ask pressure, they might ask the velocity. Okay, they might use some similar terms to confuse you, or they might ask the static head, something like that. Okay, but the thing is, the main purpose of using pitot tube is to measure the flow velocity. Okay, I hope you have that ingrained in your mind. Now let us proceed further. So the next approximation that we use is pressure at point 1 and pressure at point 1 and point 2 are considered to be almost equal. Why? Because the streamlines here are parallel to each other, are straight streamlines. There are no curvatures, so there is no pressure gradient because of the curvature of streamline. Okay, checked. Second is, you might ask, but there might be some gravitational effects because of the hydrostatic law. Of course there is, but the thing is, the distance between these 2 points are so small, that the pressure difference because of the gravity is essentially negligible. Okay, so with that approximation, you can consider the pressure at point 1 and point 2 to be equal. Okay, that is the second understanding that we have gained. So now if we apply Bernoulli's equation between point 2 and point 3, you will have, and of course they are at the same height, so the potential energy difference is negligible, right? So we will have P2 by rho plus V2 square by 2 is equal to P3 by rho plus V3 square by 2. Now since V3 is equal to 0 at the inlet of the pitot tube, So we'll have P3 to be equal to P2 plus half rho V2 square. Okay. So now and this point where the velocity becomes equal to 0 is known as the stagnation point. Okay. Again, it is itself self-explanatory. The flow becomes stagnant at that point. That's why it is known as stagnation point. Okay. Again, you use the same understanding while discussing same concept while understanding the stagnation pressure and stagnation temperature at supersonic flows when we discuss, say, compressible flow. If you study about it in the later part of your mechanics course in your university or in your BTech, so maybe you can apply the same understanding. Okay, so we will have, yeah, now let us just see what these three terms give us. So P2, as you know, P2 is equal to P1, where P1 is the pressure measured by a piezometer, and you know this piezometer gives us the static pressure. Okay, and half rho V2 square is basically dynamic pressure head because of the flow velocity. Okay, and the sum of these two is sometimes or is essentially known as the stagnation pressure head. Okay, so in other words, if you apply, say, a pitot tube, the pressure head shown in the pitot tube basically gives us the sum of the static pressure head plus the dynamic pressure head, which is the stagnation pressure head. Okay, so I hope this is clear. If there's any doubt, you can ask. You may pause the video if you're watching the recording. Maybe just take in all the discussion that we have done here. I think this is good enough. And then if there's any doubt, you can put that up in discussion forum. Okay, we'll look into it. I hope this is clear. Then we have our final topic of discussion, that is the Venturi meter. Okay, in the textbook we also discuss orifice meter actually, but for the sake of saving time, I will not discuss orifice meter. Again, let me just after discussing Venturi meter, I will discuss briefly about orifice meter, why people use orifice meter. Okay, we will briefly discuss about it, but now let us discuss about Venturi meter. Again, I will not dive deep into each and every thing that about Venturi meter. I will try to keep the discussion as minimal as possible. But if there is any doubt, you might of course ask. Okay, so just give me 2 minutes to give my throat a bit rest, and of course, and you can just look into the derivations. Maybe you will have time to write it down as well in your notes, and then we can discuss. Okay, just give me 2 minutes to just give a bit of rest to my throat. Okay. Okay. So venturimeter is a very special device that is being that is used not only as an experimental tool in our labs, but also as a very fundamental tool to measure flow rate. Okay, to measure flow rate through uh, pipes. Okay, so in many industries you will see people use venturimeter and also orifice meter to measure the flow rate through the pipe. Okay, it's the go-to device used to measure flow rate. Okay, so the structure or design of venturimeter is of this form. Like there are three major sections, that is a converging section, the throat, and a diverging section or a diffuser. Okay, so the key things to note is that the throat is usually the smallest cross sectional area, which gives us the which which has the highest velocity in that point. Okay, in that region. The converging section usually has a lower or has a lesser length comparing to the diverging section or diffuser, and this diffuser usually has a larger length compared to the converging section, primarily because to deal with the pressure losses. I think there was a detailed discussion in the class, like because of if there's a very abrupt divergence of abrupt diverging angle or this diffuser section, then the flow might start to separate in that particular region, and in that case the losses would be higher. And in order to prevent this kind of losses because of flow separation, the diffuser is usually is longer than the converging section, so that the flow can gradually expand. I don't think that's the correct term, but basically like the flow can properly follow this small diverging angle and then again resume back to its initial flow velocity. Okay, so that's the concept. Now you might ask why there is no separation in the converging section. Again, this primarily because at the converging section the flow is accelerating. When the flow is coming here, it's basically striking this income or inward bent converging section, which essentially cannot initiate flow separation. Okay, so but in this case, since the flow is decelerating, that there might be a tendency for the flow to not follow this abrupt change in the cross sectional area. They might just go in a straight line rather than following this abrupt change in the curvature. You can understand because the flow is basically decelerating in its diverging section, so there is a higher chance of flow separation. So in order to prevent that, you usually reduce the angle of diverging angle of this diffuser, so that the flow can just properly follow the curvature of the diverging section and then move back to its initial profile. Okay, so now you can see that since the velocity is higher, the pressure drop at this section would be lower. Now I think you can understand the chronology, like understand the logic now, right? Higher velocity, lower pressure. Again, boils down to Bernoulli's equation. Even if the flow is viscous, the principle applies, the logic applies. Okay, velocity at this point will be higher, so the pressure drop would be lower. Pressure at this point is higher because velocity is lower compared to the throat section, so the pressure is higher. And moreover, since the pressure at this point is lower than pressure at this point, it generates a favorable pressure gradient, so flow is towards this particular direction. Okay, I hope this concept is quite well understood, so I don't think I need to repeat it again and again. Okay, and let us say this is the datum. AB is the datum above which we measure the pressure difference. Then say that delta H is deflection of the fluid in the manometer. Then we can find the pressure difference between points 1 and point 2 using the principle of manometry. Okay, now you know why I asked you to revise, correct? So if we apply, now we have, if now we apply the boundary equation between points 1 and point 2, you get this equation, right? P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. Basically the energy at these 2 points. Let us name it as equation number star. Now using the principle of manometry, pressure at point A and point B must be same because of first the fuel are also same. Sorry, not the fuel. Fluid at point A and point B are the same and they are the same datum level. That's why the pressure at points A and B must be the same. Okay, that's the logic. Now let us just balance the pressure at these 2 points. So we have at P1 we will have, at PA we will have P1 plus rho g Z1 to be equal to P2 plus rho g Z2 rho g Z2 minus delta H plus rho m g delta H, where rho m is the fluid inside the manometer, which is mercury in this case. Okay, I think I don't need to repeat it how to obtain. You can just look into it. Okay, it's very simple. Now if you just play around with the terms a bit, you can rearrange the terms in a way something like P1 by rho g plus Z1 minus P2 by rho g plus Z2 to be equal to rho m by rho minus 1 times delta H. Well, delta is a deflection at the manometer and rho is the density of the fluid passing through the venturimeter, which is say water in this case, but rho m is the fluid in the manometer. Okay, the manometric fluid. So the reason behind using this kind of arrangement or rearranging the terms was to represent the Bernoulli's equation in terms of the piezometric head. Okay, we know that the static pressure head plus the gravitational head gives us the piezometric head. Okay, so P1 by rho g plus Z, P by rho g plus Z gives us the piezometric head. So the difference between piezometric head between the 2 points can be found out by the deflection at the manometer. Okay, now from the Bernoulli's equation, from the Bernoulli's equation, that is equation star, we can again rearrange the terms in the Bernoulli's equation to get P1 by rho g plus Z1 minus P2 by rho g plus Z2 to be equal to V2 square minus V1 square by 2g. Now you can see how we correlate these two things. Okay, so these and these two terms are the same, so that's why we will have that this term rho m by rho minus 1 by delta times delta H to be equal to V2 square minus V1 square by 2g. Okay, I hope you get it how we have obtained it. Correct? Please let me know if there is any confusion. I hope it is quite clear. Okay, these two terms from Bernoulli's equation, you get the difference between piezometric head. Again, from the principle of manometry also you get the difference between two piezometric head. Just equate these two terms, so we'll get the difference in the velocity head or the dynamic pressure head to be equal to deflection in the manometers. Okay, that is rho m by rho minus 1 times delta H to be equal to V2 square minus V1 square by 2g. Okay, so now we know that the flow rate through the pipe has to remain constant because there is no place where the fluid is being stored. Okay, so the flow rate has to remain constant, so we'll have Q is equal to A1 V1 equal to A2 V2, or V1 would be equal to Q by A1 and V2 will be equal to Q by A2. Okay, or in terms of the volume flow rate, we can write this equation as Q2 square by 2g minus Q square by 2g times 1 by A2 square minus 1 by A1 square to be equal to rho m by rho minus 1 times delta H. Okay, now if you rearrange these terms a bit, you will get something like Q to be equal to this. Okay, this equation. So from like Q is square root of 2g delta H rho m by rho minus 1 divided by 1 by A2 square minus 1 by A1 square. Okay, so basically now see, you can now find out the volume flow rate, that is Q, in terms of the things that you already know. 2g is constant, delta H you can find from manometer, rho m and rho you already know. A2 square and A1 square can be found out from the details from the manufacturer. Manufacturer will give you the details of the area of the pipe that is area at cross section area 1 and the area of the throat. So now using all the terms that you already know, you can easily find the volume flow rate. Okay, so the thing is that the main principle behind using venturimeter is that you can find out the volume flow rate by looking into a term that you can easily find out. For example, delta H can be easily found out by using a manometer. Okay, but finding out Q the volume flow through a pipe is actually very tedious task, or I would say not a tedious task, but a time consuming task. Like you may have to wait for a long time to find out the volume flow through a particular area. Maybe we'll store the fluid in a particular area and then allow it to the tank to empty to find what's the time required to fill up the tank for a certain dimension. Then you know that this is the volume flow rate of the particular fluid through the pipe. Okay, so that's again a time consuming task, and for a better working you may demand, or you may want the instantaneous value of flow rate through your pipes, right? So that's why people use venturi meter or sometimes orifice meter to find out the volume flow rates. Again, to remember, the principal task or the principal utility of a venturi meter is to find out the volume flow rate through a pipe, okay, not the velocity. Of course, one way or another velocity can be obtained, but that's not the primary task to do for us to do. The primary task or utility of the venturi meter is to find the volume flow rate, okay. Now let us just briefly discuss about orifice meter. So orifice meter is again a similar device, but rather than having a geometrically constructed converging and diverging section, what they do is they basically just place a disc-like section within the pipe, okay, like this-like opening. So it will have something like this opening. Basically is a circular opening inside the pipe. So the streamlines will get converged at the when encountering this small opening in the pipe, but the smallest area of convergence of the streamlines won't be at the orifice itself, but rather a certain distance from the orifice, okay. It will get converged at this location, which is known as the vena contracta, okay. If you study about orifice meter, you will get to know what vena contracta is, and then again it will start diverging because there is nothing forcing the streamlines to get converged further, okay. So after converging to a certain through a certain distance, because of the effect of this small opening, the streamlines will again start to diverge, okay. Then again the similar principle you can apply. You can, if you know there are some ways through which you can, if you know the orifice diameter, you can approximate the area or the region at which the vena contracta will occur. Of course, it is obtained through empirical studies. Like after thousands of experiments, they have found out that if say diameter orifice is say DO, then at a distance of 1.5 DO, you will get the vena contracta, okay. So once you do it, you can again simply apply the same understanding, do a pressure tap at this location and at the pipe where the velocity is uniform. Then do the same analogy, will end up with the similar equations. But the thing is that the level of error in orifice meter is comparatively higher than your venturi meter. First thing. Second is that the losses in the flow is again a bit higher in the orifice meter compared to venturi meter. But the thing is, the construction of orifice meter is much cheaper than venturi meter. As you can already see, it's just a simple small disc placed in the pipe, rather than a very immaculate design that you need to make to obtain this converging diverging section. So of course this is very costly compared to the orifice meter, and usually depending upon the requirement, if they can allow certain level of error in the calculation, people usually opt for orifice meter rather than venturi meter. But if accuracy is the requirement, is the fundamental requirement, then people usually go for venturi meter, okay. Of course it depends upon a choice, okay. So maybe for your understanding or for your better knowledge, you can look for orifice meter. There might be some questions in the exam, I don't know. We of course do not have in today's assignment, but you might get some questions in the exam, final exam, regarding orifice meter, okay. So just for being a safe side, you might want to look up about orifice meter. It's given a textbook. PDF or textbook can also be found out, so maybe you can just look into the internet to find the PDF or textbook. There it is discussed, okay. Now the thing is, because of the presence of viscosity, let us just read through it. Because of the presence of viscosity, the drop in the piezometric head is usually higher than what it should actually be, rather than what it should actually be when evaluated from the perspective of Bernoulli's equation. Okay, because remember, we don't actually consider the effect of viscosity while calculating the volume flow rate from the Bernoulli's equation. Okay, so because of this, but the device, the Venturi method that is working in a scenario where the viscosity is well and there, it is existing, right? So because of the presence of viscosity, this pressure drop delta S turns out to be higher. Like this delta S should be higher, representing that there's a higher pressure loss compared to what should have been that would be obtained from the Bernoulli's equation. Okay, but remember, all the calculation of the volume flow that we have done considering the Bernoulli's equation. That's why, to take into the account of the more severe drop in the pressure head because of viscosity, we need to tweak in a correction factor, usually known as the this one, coefficient of discharge. Okay, so this H actual, that is the delta H, this deflection is obtained from the experimental measurements while using the Venturi meter, is usually higher than delta H that should ideally have been if obtained through the Bernoulli's equation. Okay, and this results in the theoretical volume flow rate to be higher than the actual flow rate. Okay, so the volume flow rate obtained from the Bernoulli's equation turns out to be higher than the actual volume flow rate that is actually occurring through the Venturi meter. Okay, through the actual Venturi meter. That's why Q theoretical turns out to be higher than Q actual. So we need to tweak in a coefficient, usually known as coefficient discharge, to make it equal to the actual volume flow rate. Okay, and again, the value of this coefficient of discharge is basically the ratio of Q actual by Q theoretical, and is usually lesser than 1, and usually falls between the range of 0.97 to 0.98. Okay, and of course it has been again been found out using empirical analysis, like they have done several experiments and measurements of the actual and found out the relation between the actual and the theoretical volume flow rate, and found out that the coefficient discharge usually falls between these two values. Okay, within this range, and maybe say for a less conservative range, you can say 0.95 to 0.98. Okay, that's where it won't go below 0.9. Okay, if it's going 0.9, then there might be some calculation errors in your calculation. Okay, so that you might want to remind yourself. Okay, and that's why, like in the orifice, the value of the correction factor is usually higher. Okay, showing the higher level of error that might occur while measuring the volume flow rate through the orifice meter. Okay, so let us take an example. We have that the diameter of the pipe to be 26 millimeter and diameter of the throat to be 16 millimeter. Okay, then the fluid that we have used in the manometer is mercury, so the density is 13,600 kg per meter cube, and the deflection in the manometer is found out to be 5 millimeter. Let us say the tank at which the fluid is being filled is, say, of area 759 to times 455 millimeter square, and the time at which the tank is being filled is, say the time to empty the tank is, say, 1 minute. Okay, and the height through which the fluid has been emptied is 40 millimeter. Okay, so you get an idea, right? There is a flow rate to the Venturi meter. The fluid is being stored in a tank. Say when the fluid reaches a height of 40 millimeter, the opening is being opened so that the fluid starts to fall out from the opening, and the time required, like if you find that, and if you just do something like the volume of the water in the tank divided by the time, will give you the actual volume flow rate. This is how the volume flow rate is usually found out, the actual volume flow rate. Okay, so From this data you can find the actual volume flow rate, right? The volume of the tank, what volume of the water in a tank would be area of the tank times the height of the tank, what height of the water in the tank, and the volume flow rate would be volume of the fluid divided by time, that is 1 minute in this case. That will give you the actual volume flow rate. Okay, now you need to find the theoretical volume flow rate using these parameters. Okay, sorry, using these parameters in hand. Okay, there also you can find out because we know the equations. From that you need to find out CD, which will basically be Q theoretical by Q actual. Okay, Q actual by Q theoretical, I'm sorry. Correct? Yeah. So let us now look into it. So we know that the theoretical volume flow is given by this equation. Okay, we already just found out. And we know A1 is this, D1 is given, so we can find out A1, D2 is this. So if you substitute the value of A1 and A2 in this equation, you can get Q theoretical as, and of course, rho Hg is 13,600 kg per meter cube, rho is 1000 kg per meter cube, rho is water in this case, and delta H is 5 millimeter, basically 0.005 meter. Okay, the deflection is 0.005 meter. So if you substitute the value of A1, A2, delta H, and rho in this equation, so you will get Q theoretical as 2.4135 times 10 to the minus 4 meter cube per second. Okay. Now the actual discharge is given by the volume of the water inside the tank and divided by time required to empty the tank. That would be 759 times 455 times 40 divided by 60. Of course, this is into 10 to the minus 9 again to find out in terms of meter cube. So you will get Q actual to be 2.3023 times 10 to the minus 4 meter cube per second. Okay. So if you do that, you can get CD as Q actual by Q theoretical. You will get CD to be equal to 0.953, which is again within the conservative range of coefficient of discharge. Okay. So if it's all fine, now let us take some examples. Okay. Okay. So yeah, let me just go back. I think we missed. Yeah, this is the example. Okay. I hope the question is visible. So since there are very few students in the class today, so what I will do is, again, I will follow the same steps that we follow when there are very few students in the class. So what we will do is, I will discuss the question. Then all the students who are watching the recording might pause the video for a while, think about their answer, and then let us know, then compare their answer with my discussion. Okay, I hope that is fine. So that would be beneficial for all of us, right? The viewers as well as me, and the participants as well who will be watching the video later for their reference. So we can do that, right? So the first question is, a stagnation point is a point in a fluid flow where 1. Enthalpy of the fluid is 0, 2. Velocity of the fluid is 0, 3. Static pressure is 0, 4. Stagnation pressure is 0. Okay. So I think it's very simple. So the term itself, stagnation itself, gives us the hint. Anything that is stagnant, which means that it's not moving. And if it's not moving, the velocity of that particular object would be 0. So stagnation point in the flow field would imply the velocity of the flow is 0. Okay, it's very simple. So I don't think even we need to pause the video. I think you will already know what it is. Okay. Question number 2 is, the diffuser angle of a venturimeter is less than the converging cone. 1. To minimize the loss of energy due to flow separation. 2. To increase the velocity of the flow in the direction of the flow in the diverging section at the diverging part. 3. To decrease the pressure in the velocity in the direction of flow at the diverging part. 4. To avoid the situation where flow may become compressible. Okay. So I think we know the answer, but it would be better for the students to just look into the options and just look into it whether some other options are also valid or not. Okay. So who are trying to answer may pause the video now. So now I will answer the question. So again, answer is very simple. The options might try to trick you, but the correct answer would be the first one, that is the correct answer, that is to minimize the loss of energy due to flow separation. Okay. So other option 2 is not correct when we are not increasing the velocity at the diverging part, of course. We are not decreasing the pressure as well in diverging part. So 2 and 3 are again not correct. 4 is also not correct because the flow is not at all in a regime where compressible effects can be considered. So again, option 4 is not correct. So option 1 only turns out to be the viable answer. Okay. Question number 3 is something that we need to do some calculations. So let us just look into it. A steady two-dimensional velocity field is presented by the following stream function. Okay. Psi is equal to ax square y, where a is a non-dimensional constant. Okay. The flow can be assumed to be frictionless. Now consider 2 points, say P14 and Q21 in the flow field. Which of the following statements are correct? The flow is irrotational. That's the first question. The flow is irrotational. That's the first question. Second is, the steady state boundaries equation can be used to evaluate the pressure difference between points P and Q. Okay. Option 3 is the steady state boundary equation can be used to evaluate pressure difference between points P and Q since the flow field is irrotational. Okay. And the fourth option is the steady state boundary equation cannot be used to evaluate the pressure difference between points P and Q. Okay. So anyone trying to answer the question might just stop the video for now, because now I'll start discussing the answer. Okay. You may stop the video now, so start discussing the answer. Okay. So to look into the answer, it's again, first of all, you need to again start with our basic understanding. You have the stream function psi, and since you're dealing with Bernoulli's equation, you cannot deal it with using the stream function, at least for the simplistic case. You need the velocity components, right? If you know psi, you know that the flow field has to be incompressible and 2D, so you'll have two velocity components. So from there, let us find out the respective two velocity components. Okay. So we'll have u as dou psi by dou y, that is equal to ax square, and v as minus dou psi by dou x, that is minus 2axy. So the first option was whether the flow is irrotational or not. Okay, so let us find del cross v. So del cross v will give us minus 2ayk, which tells us that the flow field is not irrotational. Okay, it may be irrotational if y at y equal to 0, but it's not irrotation everywhere. Okay, so in general, the flow field is rotational. Okay, it's not irrotational. So now let us check. So we cannot apply Bernoulli, but the flow field is steady, of course. That's fine. Flow field is incompressible because stream function tells us that the flow field has to be incompressible. Then what's the next thing? Flow is inviscid, frictionless. They already told us. Correct. Let us just write it for your flow is frictionless, inviscid, steady, incompressible because of the definition of stream function, now to apply Bernoulli's equation, the other thing was that the 2 points at which we want to measure the pressure difference, or we want to apply the Bernoulli's equation, has to lie on the same streamline. So if the 2 points are on the same streamline, the value of the function, the stream function, will be same. Correct. So let us check whether these 2 points give us the same stream function or not, same value of stream function or not. So psi at point 1 and 4 would be a 1 square times 4, would be 4a. Similarly, psi at 2 1 would be a 2 square times 1, that is 4a. So you can say that point P and Q lie on the same streamline. So it lies on the same streamline as well. So it just tells us that then we can easily apply now Bernoulli's equation to find the pressure difference between the 2 points P and Q because all the 4 conditions are satisfied. Okay, but what we cannot do is we cannot apply the boundary equation at point P and Q if the P and Q were not on the same streamline, because the flow field is rotational. Okay, so that's what we need to remember. So, okay, so this is the answer. So the correct answer would be option B, that the steady state boundary equation can be applied to evaluate pressure difference between the points P and Q because they lie on the same streamline. Okay, this is flow field is not rotational. The flow field is not irrotational. Again, this is not irrotational, so it is also incorrect. Okay, and it's not that we cannot use boundary equation, we can use, so this is also again incorrect. So this question for me I feel was a very conceptually heavy question. Like there are many concepts that you need to inherently know without in fact things being given. Like they are not explicitly told that the flow is incompressible or steady state. From the velocity field you need to determine whether flow field is steady state or not, and then from the definition of your stream function you need to know that the density is constant. Then only you can apply the think of applying the boundary equation. Okay, so I hope it was clear. If so, then let us proceed further. Okay, let's look into the next question. Okay. Question 4. A piezometer and a pitot tube are tapped into a 4 centimeter diameter horizontal water pipe at heights, and the heights of the water columns are measured to be 20 centimeter in the piezometer and 35 centimeter in the pitot tube, both measured at the top of the surface. Determine the velocity at the center of the pipe. Okay, I think again it's very simple. Why? Because we know that these two give us a different pressure heads. One gives us the static pressure, one gives us the stagnation pressure. So the pitot tube gives us the stagnation pressure head, that's why it is higher than the static pressure head given by the piezometer. So if you find a difference, you will easily get the velocity. Okay, so anyone trying to solve the question again might pause the video. Okay, so I'll just show the answer for now. Okay, because there are very few participants, sorry for not involving the participants now, but if they're just watching the recording, maybe you can just pause the video and then look into the solution. Okay, so the solution for it would be simply we have the piezometric pressure head to be 20 centimeter and the static pressure head to be from the pitot tube to be 35 centimeter. Now if we apply boundary equation at these 2 points, we'll have P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2. Now these two are the same horizontal level, so Z1 equals Z2. So we have V1 square by 2 is equal to P2 minus P1 by rho g. So we have rho g times H pitot plus R minus rho g plus H piezometric plus R, if R is the diameter of the pipe. But R will get cancelled out in both the cases. Okay, that's again fine. So you can easily tell V1 to be equal to 2g times square root of 2g times H pitot minus H piezometric. Again, just be consistent in the units because these are in centimeter. The piezometric heights, sorry, the pressure heads are in centimeter. Just convert it into meter to get the correct answer. So you will get V1 as square root of 2 times 9.81 times 0.35 minus 0.2, or V1 to be 1.72 meter per second. Okay. Now let us look into the next question. Okay. So it's a bit lengthy question, so I will zoom out a bit. I think then okay, maybe it's fine. Air at 110 kilopascal and 50 degrees Celsius flows upward through a 6 centimeter diameter inclined pipe at the rate of 45 liters per second. Okay, you need to convert it into meter cube per second. Okay, you need to know the relation between liter per second and meter cube per second. The duct diameter is then reduced to 4 centimeter through the reducer. Okay, basically the throat. Densities of air and water are given to be 1.19 kg per meter cube and 1000 kg per meter cube respectively. Pressure change across the reducer is measured by water manometer. So your manometric fluid is water in this case. Okay. The elevation difference between the 2 points on the pipe where the 2 arms of the manometer are attached is 20 centimeter. Okay. Maybe when we look into the diagram, it will be much clearer. So basically, there is an elevation difference between the 2 points. So the potential head are now not equal. So there would be a difference between the 2 points. Okay. Determine the differential height between the fluid levels in the 2 arms of the manometer. So you need to find the deflection, height deflection in the manometer. Okay. So just for completion, let us look into the diagram as well. So this is the diagram in hand. So we have point 1 and point 2 as it is shown here. Okay, and these two are different levels. That's why you have Z2 would be higher than Z1. Okay, just for your reference, at 20 cm higher than Z1. You need to find is this deflection H. Okay. So anyone trying to find the solution might pause the video now. You can maybe draw the diagram. I have not drawn a diagram in the solution, so you can draw a diagram for your reference. Okay. So if it's done, then let me just proceed further. Okay. So again, it's simple. We need to again apply Bernoulli's equation between these 2 points. So we'll have P1, this apply Bernoulli's equation between the 2 points. If you simplify this equation a bit, you will have P1 minus P2 by rho g to be equal to V2 square minus V1 square by 2g plus Z2 minus Z1. Now what would be rho? Here rho would be the fluid passing through the venturimeter, which is air in this case. So we'll have P1 minus P2 to be equal to rho air minus V2 square minus V1 square by 2 plus rho air times G Z2 minus Z1. Usually this term we neglect because venturimeter is usually kept horizontal in our analysis, but in this case it's not kept horizontal, it's inclined, so there is a finite value of Z2 minus Z1. Okay. Now V2 minus V1 can be found out by, since the volume fluid is given and diameters are given, so you can find the value of the velocities at the pipe and the velocity at the throat. Okay. So we will have V1 as 4q by pi d1 square, that is 15.92 meter per second, that is at the pipe. Then at the reducer, that is at the throat, you will have a higher velocity because of the lesser area. You can get V2 to be equal to 35.81 meter per second. Okay. Just remember to convert q in terms of meter cube per second rather than from liters per second. Okay. Now Z2 minus Z1 is 0.2 meter. If you remember, Z2 was at a higher level than Z1 from the diagram. It was 20 centimeter higher, it is 0.2 meter. Okay. And rho air is 1.19 kg per meter cube. So if you substitute these values in this equation, you will get V1 minus P2 to be 614.53 pascals. Okay. Now we know that the deflection in the manometer would be equal to rho W G times delta H, that is the deflection in the manometer. So from this you will get delta H to be P1 minus P2 by rho Wg, or delta H to be equal to 0.0626 meter. Or simplifying it, you will get it is equal to 6.26 centimeter. Okay. So the correct option here would be option number 1. Okay, 6.26 centimeter. Okay, I hope the example was clear. Now let us just look into the final example for today's class. Okay, a pitot tube is inserted in an airflow at standard temperature and pressure. STP is standard temperature and pressure, to measure the flow speed. Okay, pitot tubes used to measure the flow speed. The tube is inserted so that it points upstream to the flow, and the pressure sensed by the tube is the stagnation pressure. Of course, pitot tube measures the stagnation pressure. The static pressure is measured at the same location in the flow using a wall pressure tap, and the specific gravity of the liquid mercury is 13.6, and the density of water is 1000 kg per meter cube. Density of air at the standard temperature pressure is 1.23 kg per meter cube. If the pressure difference is 20 meter mercury, the flow speed is found out to be, okay. So the thing is, you are using pitot tube to measure the airflow. Okay, so the density of the fluid at which the pitot tube has been inserted is air. Okay, so that's why just don't get confused. So you need to use the density of the fluid in this case to be the density of air. Okay, the rest everything else I think is very simple. Just again simply apply Bernoulli's equation between the 2 points. Okay, so we have the pressure deflection, the pressure measured by the manometer, which has mercury as the manometric fluid, is rho G times H times G, which is 2670.72 pascals. Okay, now from Bernoulli's equation, applying Bernoulli's equation, you will end up with the same equation, that is delta P to be equal to half rho air times V square. Okay, or V to be equal to 2 times delta P by rho air, or 65.86 meter per second. Okay, I think you know how we obtained it. This equation is very simple. P1 by rho plus V1 square by 2 is equal to P2 by rho plus V2 square by 2. If V2 is the point at which tension, V2 is the point at which the pitot tube has been placed, so V2 would be equal to 0. V1 would be equal to square root of 2 times P2 minus P1 by rho, which is rho air in this case, and P2 minus P1 is found out by using the pressure difference obtained from the manometer, which has mercury as its working fluid. Okay, that's what we do here. So from that we get V as 65.86 meter per second. So correct option would be option number 2. Okay, so if I hope this discussion was helpful for you all, or whoever has participated today in the class. Thank you for that, and anybody watching the video as well, please let us know your review. Like if there's any doubt, if there's any pending doubt you want to clarify, you can put that in discussion forum. We will take that in the next class. Okay, so that's all for today from my end. Hope you have a great week ahead, and let's all meet in the next week. And I'm really excited for next week because we will be discussing about the fluid dynamics part, starting with the Reynolds transport theorem, and the final topic or final portion of this course in the last 4 lectures. So I'll make sure that it's very engaging and helpful for everyone. Okay, so with that, let's end today's class and have a great week ahead. Okay, thank you.